Hello, this is E637 and I'm Charles Bouman, and we're going to talk about filters today. So we started on filters last time. We're going to pick it up. Let me just quickly ask, are there any questions? Is everything coming along with the labs? I've noticed a few people have pointed out some minor corrections and things. Yep.
Or we can implement C++.
Okay, so the question is, shall we stick to ANSI C? Oh, I guess it's recorded, right? You guys have microphones. Mm-hmm. So ANSI C, or can we use C++? Yeah, you can use C++. I mean, use ANSI. I would stick to ANSI C++. There is an ANSI C++, right? Yeah, it didn't used to be, but there is now. Sure, that's fine. I know that a lot of people are more comfortable programming in C++ these days. I'm sad and embarrassed to admit that I can't really program in C++. Oh, God. I guess what I'm going to have to do is take a sabbatical to learn C++ or something. But I'd actually have to become a graduate student, because otherwise I couldn't actually force myself to learn it. I have to have an assignment due. Okay. All right. Okay. Any other questions? Okay. So we're going to talk about filters. I'm sorry. I'm going to have to take off my sweater. It's a little too warm in here. Okay, filters. So we're first talking about FIR filters. I started to talk about that a little bit last time. In an FIR filter, basically you have an n by n window, and you slide the window over the object. What happens is that there's a point spread function. So the point spread function is what you get if it's the impulse response. If you put an impulse if your image is just a single point, like a star, then what will come out is the point spread function. So if the point spread function is h of k L, okay, then the output will be the convolution of the point spread function with the image. So convolution, as you I'm sure know, requires that you do this flip and shift thing, okay, because of the fact that you have the minus signs here. So you're summing over the k index, and you have minus k here. So the x's can be viewed as being shifted or flipped and then shifted. So and convolution is commutative, or it's So convolution of h with x is the same thing as convolution of x with h. So you can view the flip shift occurring with the h. So what happens is that if you have an image, if that's, say, the point spread function, right, then to convolve, you take the point spread function and you flip, okay, and then you shift. So once you flip, then you do the inner product. Ignore the 1/16 there, because that's the scaling factor. You multiply corresponding values, you sum together, and then you shift. Now, actually, this window is like coarser. Oh, I guess I can apply it to here. Hold on just a second. This is a little bit clearer. So here, let me do the flip and shift. I'll filter this image right here. So the way I filter it, that's my point spread function. So if I put an impulse into my filter, I get this out by itself. Oops, that out by itself. Okay. Notice in this particular case, this is just a specific example. It's got ones in the corners, twos, and then these are these are called the nearest neighbors. So that's the center point, and the 4 points that are nearest are called the nearest neighbors, and then these are the corner points. And now to convolve with this, I flip it. When I flip it, I first flip along that axis. See? First flip that way, but that's not good enough. I have to flip this way too. And now guess what? A flip by two flips like that is equivalent to a rotation. All right, so I do this, and then I convolve by shifting. So now it turns out for this particular example I'm going to do, why am I dividing by 16? Because if I add these numbers all up, there's a 4 in the center, plus then there's 4 2's, so 4 times 2 is 8, and then 4 1's, so that's 4. So this is 4 plus 8 plus 4, so it's 16. So if I divide by 16, why would I divide by 16? Because then the DC gain is 1, right? Because the integral of the point spread function, or the sum of the point spread function, is what? It's the what?
DC component.
It's the DC gain of the filter. It's the value of the transfer function at frequency 0, right? So typically you want the DC gain to be 0 because you don't want the image to get any brighter or darker. You just want to change its frequency content. Okay? So I take this guy now and I flipped and shifted it, and now I can slide. So if I'm over here in the 0 place, I get 0 out. 0, 0, 0. Like, oh, no, 0. I don't get a 0 there. Actually, that's the first point I don't get a 0, right? Because that 1 is over top of the 16. So I get 16 divided by 16, so I get 1. And that's the 1 I get right there, right? Then over here, I get 2 times 16 plus 1 times 16, so I'm going to get 3. Right? And if I come over here, well, what's the value that I'm going to get there? Well, if the DC gain is 1, and all these values are 16, and so I know this has to come out to 16. Now, if I get down here, now what ends up happening is I fall off the edge of the image, and the signal starts to get attenuated. This is a blurring filter because it's smooth, so its gain at higher frequencies is going to be lower. So let's see. So this is this example. Here's another example. This is a different filter. Here, this filter, in this impulse response, it kind of looks like a bright edge. Now, if you could have, images can only be positive. Okay, so you can't have a negative image, but if you added a constant, then this would be bright and this would be dark. Now, when you do the flip and shift, you get this, right? So now what happens is that this is the positive value in this direction. So you're adding a bunch of values here and subtracting a bunch of values there. Now, this is 2 plus 4 plus 2, so that's 8. So you divide that by 16. So what it looks like is you're really taking 1/2 here, and then you're taking 0 here, okay? And you're taking minus 1/2 here. So that's like you've taken, if this is a sequence in time, this would be x of 0, say this is x of, or so make this x of n, this is x of n plus 1, this is x of n minus 1, right? Then this is x of n plus 2, dot, dot, dot. This is x of n minus 2, dot, 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 dot. So this is the sequence in time, okay? And if I add those, then what I'm doing is I'm getting x of n plus 1 minus, times divided by 2, minus x of n minus 1 over 2, right? Well, that's equal to x of n plus 1 minus x of n minus 1 over 2. Well, that's approximately, if this was a continuous function of time or space or whatever, then this would look like dx of n dn. Of course, I can't really differentiate x of n because it's not a continuous function of time. But if I sort of pretended it was, this is an approximation to the derivative. Or if this is a sampled version of an underlying continuous time signal, then this is an approximation to the derivative. Okay? So computing this filter is like computing an approximation to if you have f of, okay, hold on for a second. I guess x is going to be this way and y is going to be that way, okay? So if this was f of x, y, this looks like you're computing df dx. You're taking the derivative in the x direction. So you can use filters to approximate derivatives in the x direction. And if you do, I won't bother doing the flip and shift on this because we just did it on the last one. It's pretty much the same thing. You can do the same thing with derivatives in the y direction. Now, there is a little detail to be considered here, which is which direction is positive y. So we're going to say this is y, and this is x, okay? So convolution with this guy is going to approximate df of xy dy. So that looks like the derivative in the y direction. And sure enough, I forgot to show you the result of the filter. If you apply this filter, look what you get. You only get output along the horizontal edges. Because the derivative in this, if you have an image that looks like this, right? Okay. And you have lines in it like this. And you take the f of xy dy. Well, the derivative here, it's constant in this direction. So the derivative in the y direction is 0. So you won't see anything. But so the result here will be like this. It'll just be empty, right? But if you take this, if you have some lines like that, well, the derivative there will be large, so you'll get this. So differentiating, so I should put it here, dy. Differentiating along the y direction detects horizontal edges. Differentiating the same image, if it's differentiated along the x direction, dx, you get vertical edges, right? So if this gives you horizontal edges and that gives you vertical edges, the obvious thing to do is put them together, okay? So what you could do is this. I'm jumping ahead a little bit here, but I can't help myself. If you take the gradient, of f of xy, right? The gradient's a vector. So it's going to be like df dx, comma, df dy. So this will be vertical edges, and this will be horizontal edges, right? So what I can do is I can take the magnitude of this vector, right? And this will be the combined result, which will be df dx squared plus df dy squared square root. And that's actually a lot of computation because you have to square them. Squaring is pretty easy, but taking the square root is a fair amount of computation. Another possibility is you could just take f norm squared, and that way you don't have to take the square root. Okay, so filters are useful. Each of these derivatives is a linear filter, and then you combine the two linear filters non-linearly by squaring them and adding them. Squared will basically take magnitude, because this can be a signed quantity. You can get a negative value when you apply this edge filter, right? And in fact, we did. Let's just check here, see where the negative values are. Now, the negative values, okay, I set it up so the values were positive, but here along the edge you get some negative values. Yeah, question?
So, find the bridges and the values of the image.
Bridges and values, yes. We're going to talk about that in a minute. The ridges are like local maxima, and valleys are local minima. So you want to be able to distinguish between those. Let me get back to you on this, okay? Because we're going to talk about basically what you want to do is combine this with some other operators. Because first of all, so if you want to do edge detection, we're going to talk about edge detection. But if you want to do edge detection, you can. I'll just tell you the answer and then we'll come and do it again later. But if you want to do edge detection, you might want to say, well, I'll take the gradient of f, okay, and say, well, I'll compare it to some threshold value, right? But the problem with that is that you're not sure how to pick the threshold value. So then you might say, well, I'll take the maximum. But then you say, well, the maximum over what area? This needs to be a local maximum. So another possibility is to say, well, I'll wait for the second derivative to be 0, because when the second derivative is 0, it means that the first derivative must have reached a local extrema, right? Either a minimum or maximum. So, so you could also do this, right? So that's a typical edge detector, but the problem is this will detect both peaks and valleys, as you said. So usually what you do is, a simple thing to do is to take that and combine it together with the criteria that the gradient of f of t squared has to be greater than some threshold. So you have both conditions. Okay? All right. But, there's lots of edge detectors. Let me see. Now, this is just an example. In fact, you did something like this, I think, in the lab, where some filters, 2D filters, are separable. And if they are separable, that's advantageous because they can be implemented with much less computation. But here it's just an example that we have this is a separable filter because it's the product of two filters. If you take the filter which is, the 1D filter, which is impulse response 1, 2, 1, and you multiply, and then you make h of mn equal to h1 of m times h1 of n, then that's a separable filter. And essentially what happens is that you get the values, let's say 1, 2, 1, 1, 2, 1. And each value here is formed by multiplying them. So you get a 1, 2, 1. Here you get a 2. Here you get a 4, 2. And this is 1, 2, 1. So this is the filter you get, which is sort of the separable extension of the 1D filter. And then you can calculate the Fourier transform of the 2D filter by taking the continuous discrete time Fourier transform of each 1D filter and then multiplying them together. So doing that, you get this expression here. You can plot it. You guys did this for the one of the labs, or something very similar to it. And this is the result you get. So you can look at this. And one thing that's interesting is that the gain at pi, so if you plot the frequency response over the range, so this is mu, and this is nu, okay, and this is pi, and this is minus pi, and this is minus pi, and this is pi, okay. Oops, I was supposed to go through there, okay. Any place along this boundary, it's 0, because if you look at this function, h of e to the j mu e to the j nu, that's equal to 1/4 1 minus cosine of mu, and this is this is plus cosine of nu. So over here, this is mu equals pi. This is mu equals minus pi. This is mu equals pi, and this is mu equals minus pi, right? So if either of those conditions are true, if mu equals pi, then cosine of pi is minus 1. So for mu equals pi, or plus or minus pi actually, then cosine of mu equals minus 1, and h of e to the j mu e to the j nu equals 0. So all along this boundary, the gain of the frequency of the transfer function is 0. So if you look at this, you see, yeah, okay, that's correct. It's 0 there. But at DC, it's 1 because the impulse response, well, I can either evaluate this here, that cosine of 0 is 1. So this is 1 plus 1, which is 2. So 2 times 2 is 4. Divided by 4 is 1. So that works. The other way of looking at it is if I sum these variables here, this is actually divided by 1/4. So this whole thing is divided by 1/16. I add these. I've done this already. It's 4 plus 4 times 2 is 8. So that's 12. Plus 4 is 16. Divided by 16 is 1. Comes out to the same thing. Okay? It seems like really trivial now because now you know it. It's funny how things are. When you know them, they're really easy. And when you don't know them, they're really hard. Okay, so 2D FIR filter. This is an interesting example. Okay, interesting example. So I can't help myself. I'm going to have to get ahead of myself because I do enjoy getting ahead of myself. So what happens is that I could do the following. I could say, if I have a signal x of n, so I have x of n minus 1, x of n plus 1, okay? And I can say, well, let's say I want to compute the approximate derivative here. So I want to compute dx dn evaluated at n equals 1/2. I know this is nonsense, okay, because this is a discrete time signal. It doesn't have a value halfway in between, okay? But I'm thinking, okay, bear with me for a moment here. I'm doing an approximation to a derivative, and this xn I'm thinking of as being samples of a continuous time function, okay? So if I were going to approximate this derivative, what would be a reasonable thing to do? Well, I'd take x of n plus 1, and I subtract x of n, and I divide by 1. And that would be the derivative at this point, right? Does that make sense? I'm seeing some faces that seem a little bit perplexed, right? So if I take this, so what you could do is see, it could be x of n here is equal to some underlying signal, s of nt. And then this is s of n plus 1t. See, because it's a sampled signal. And let's assume that the signal's smooth in time. X of n minus 1t, right? So now what happens is that if I want to approximate the derivative of s, we better make t equal to 1 here. But if I want to approximate the derivative of s, I just take the difference between these two things and I divide by 1, which is their spacing. And that's like the derivative. And I've taken the derivative at the halfway point, right? Okay, it's logical enough, right? And the derivative at this halfway point here would be xn minus xn minus 1 divided by 1, right? Okay, fine. Now, if I want to compute the second derivative, so I want to compute d squared x dn squared evaluated at n equals at n, okay, this is n plus 1/2, and this would be just at n. Okay, well, to do that, what I do is I take x dx dn evaluated at n plus 1/2 minus the x dn evaluated at x minus 1/2, right? And I divide by 1. Well, I calculated those, because that's this, right? And this is that, right? So I get here x of n plus 1 minus x of n. And I get minus x of n minus x of n minus 1. and I divide that all by 1, so it doesn't really matter. So I get here that I get x of n plus 1 minus 2x of n, and then I get plus x of n plus 1, right? So I can just rearrange some things here. I get minus 2 times x of n minus 1/2 x of n plus 1 minus x of n minus 1. Right? So I get this. I get the following relationship. That the derivative, the second derivative, equals approximately, I'm not exactly sure what that means, okay, because you can't differentiate this thing, okay, but thinking of it as an approximation to a continuous signal, I mean, this could all be made very precise. Then that's equal to minus 2 times x of n, I'm just going to rewrite what I had before, right? But then the other way to put this is that it looks like minus 2 times, I take x of n minus the average of x of n nearby. So this is like this is the sharp part of the image, because I've taken x and I've subtracted its average local value. This is the sharp part. This is the unsharp mask. Okay? This is the unsharp mask. This is like the not unhappy. Okay? I've removed the unsharp part. So this is just the sharp part. This is the sharp part. Right? So the second derivative gives you the sharp part of the image. So this is kind of handy. This comes up a lot. If you generalize this to 2 dimensions, then you get that. If you have a function of x and y, or I'll make it m and n, okay? And I want to generalize the Laplacian. If you recall, the Laplacian is equal to d squared f dm squared plus d squared f dn squared. So in this case, you would generalize this by just adding these together. So what ends up happening is this looks like minus 4 times xn minus 1/4. This becomes mn. This becomes x of m plus 1n plus x of m minus 1n plus x of m n plus 1 plus x of m minus n minus 1. So this is just the 2D average of x m n. So whenever you subtract a pixel from its local average, you're really computing something proportional to the Laplacian. This is called the Laplacian. You're computing something proportional to the Laplacian. So if you subtract a pixel from it, if you take a pixel and subtract its local average, what you get is minus 1/4 the Laplacian. It's just, so it's off by a sign and a fixed scaling component, okay? But it's basically the same thing. The scaling component would have changed anyway, depending upon what the sampling units were. because if you were sampling in units of t, then your derivatives would be off by some scale factor anyway. So the sign is the only relevant thing, and usually that doesn't even come up. And actually, now I'm really getting off into a tangent, but I'll say it anyway. I don't know how many people have ever taken an electromagnetics course, but there's this is a really standard equation to solve, right? Where this is the equation you solve for finding the potential in the potential field with boundary conditions, right? So if you have a box, a metal box, and you put a voltages, so you have an insulator here, right? And you have plus minus like this, right? And you put an insulator here, otherwise it would short out, right? So and then maybe you ground this, okay? Or I don't know. You could make this whole thing all one connected together. Then the electric field in here is solved by solving that equation, which is more or less the same equation you use for solving a thin membrane problem, like you would get if you have a bubble, right? If you pull a bubble across the surface. So this is a very standard equation that gets solved for a lot of problems. It's similar to the equation you'd get for the deflection of a rubber band with a force. Okay, so this is a real standard equation, and if you're doing that equation is the same thing as this equation, right? So if you want to solve Laplace's equation in 2 dimensions, you're basically just trying to set xmn minus the local average of xmn equal to 0. So this comes up a lot, okay? It's like a smoothness constraint, basically. And in one place it particularly comes up, I just mentioned a moment ago. Let me see if I can find this slide so you'll believe me. Is here in edge detection. So this is actually usable. So this is the criteria you want to set. You want to look for points where this is 0 when you're doing edge detection. We'll talk about this in just a moment. It's the next topic soon after filtering. So this comes up a lot, okay? So that's one reason we're looking at this, because this is a Laplacian operator right here. It's taking a local average of the pixels around it. Now so the center pixel here is multiplied by 4, and then the outer pixels are minus 2 times 4. So 2 times 4 is 8. Then so it's minus 8 plus 1, 2, 3, 4. So that's minus 4. So you're taking a center pixel and computing the average of its neighboring pixels and subtracting them, right? So this computes something that's proportional to the Laplacian. This is basically a Laplacian operator. It comes up a lot in imaging applications. And it's a high-pass filter because, remember, we're taking off the unsharp component, right? So when we subtract the x from its local neighbor, what we get is the unsharp mask, which is the sharp part. So we throw away the DC. In fact, if you look at this filter, you sum it up, this is 4 on the outside plus minus 8 is minus 4, plus 4 is 0. So these pixels add to 0. So you know the DC gain of this filter is what? If the pixels add to 0, the DC gain is what? 0, okay? Gosh, you guys are good, okay? I got you trained. Remember, the 4 answers to all questions, 0, 1, 2 pi, and then after that it kind of gets fuzzy. All the above. E, you can throw that in there. Cosine theta comes up quite a lot, okay? Okay, now, but 0 and 1 are good starting points. Now, at 0, the gain is 0, see? And here, what's the gain at 1, at pi? It's 1, okay? And we can see that too because, here's some intuition. What does it mean if I calculate, if I'm asking for e to the j pi, okay? Oops, pi. So that's the same thing as e to the j mu, e to the j mu, where mu is equal to pi and mu is equal to pi, right? Okay. Now, what's the intuition behind that? Well, one possibility is just to evaluate the Fourier transform, okay? If I go back and do that, okay, what was the intuition when I evaluated a mu and nu equals 0? In that case, if it's h of e to the j 0, e to the j 0, what's that equal to? That's the dc, which is the sum over m and n of h of mn, right? It's just the area under the kernel, right? So what's the intuition here? It's the gain at frequency pi pi. So what's the frequency pi pi? So let's think about this. This is a very good problem, okay? This would be a good exam problem, actually. Let's do the 1D case first. And if you have the frequency associated with e to the j pi, what's that? So it's e to the, okay. So if you have the frequency e to the j pi n, right? Frequencies in 1D are e to the j omega n, right? That's a pure frequency. Call that x of n. That's a pure frequency, right? So if the frequency is pi, then I get this. And what's this equal to? It's, well, what's e to the j pi?
-1.
It's -1, right? Let me just check for those who are a little rusty on this sort of thing. E to the j pi, this is real, right? And this is imaginary, right? So e to the j 0 is 1. And then I go pi. So pi is 180 degrees, right?
Yep.
So the vector's pointing that way. So e to the j pi equals -1. You know what? I just remembered something. When I was an undergraduate, I actually I know this is a really nerdy thing to do. Okay, what can I tell you? I should be embarrassed, but my roommates and I actually put that on our wall because we thought that was a very interesting relationship. What do you want? Okay? There's no accounting for taste. But it is really quite amazing that that's true, okay? I mean, e to the j pi is -1. It's a very amazing thing, right? I mean, you got to really enjoy life when you see something like that. You think to yourself, wow. Okay, but anyway, getting back to the point, if e to the j pi is -1, then this whole thing is -1 to the n, right? So this thing here is a sequence 1, -1, 1, -1, 1. And guess what? That is the highest frequency you can have in discrete time, because you can't oscillate any faster than completely flipping every time. It's like every time somebody asks you a question, you change your mind. Well, I think I'll wear the pink shirt. No, I think I won't wear the pink shirt. I think I'll wear it. So you can't change your mind any more rapidly than that. This is as fast as you can. In 2D, what's the most rapidly you can change your mind? Well, you have 1 in the center, and you go -1, 1, -1, 1, right? You go -1, 1, -1, right? Now, in the other direction, you go -1, 1, -1, -1, 1, right? Then this goes +1, +1, +1. It's a checkerboard. So the checkerboard's the highest frequency you can have. Okay, minus. So let me I'll do that again, just to make it a little clearer, perhaps. So you have plus, minus, plus, minus, minus, plus, minus, right? And this is minus, plus, minus, plus, minus, plus, plus, minus, minus, plus, minus, plus, plus, minus, minus, plus, right? This is plus, minus, minus, plus, plus, minus, plus, minus, minus, plus, plus, minus. So you get a checkerboard. That's the highest frequency you can have in 2D, in discrete space, right? Now, if you take that function, you take its inner product with this, what are you going to get? You'll get 4 in the center, then the minus 2, let me just, okay, you'll get 4 minus 2, minus 2, minus 2, minus 2, 1, 1, 1, 1. All the other ones are 0, right? So what will happen is the center one will stay 4. These will turn to 2, 2, 2, 2, and this will 1, 1, 1, 1, right? So that sums to what? 16. Then you divide it by 16, because if you remember, our definition here was that this was 16H. So these are all have to be divided by 16. And what's 16 divided by 16? 1. So there you get the intuition that, guess what? That's 1. You may not be able to see that, but that number there that's very small is 1. So the gain is 1 at pi. But it's not 1, it's 0 if only one of the frequencies is pi. Because, let me see, I could do that too. If I only do the alternation along the rows and not the columns, then I'll get 1 minus 2. Oh, no, I'm sorry. This will be plus, this will be minus, this will be minus 1. And this will be minus 2, 4, minus 2. And this will be minus 1, 2, minus 1. So let's see what that adds up to. That's 4 plus 4, so that's 8. Minus 4 is 4, minus 4 is 0. So it's 0 over 16 equals 0. So at mu equals pi and mu equals 0, so that we have that h of e to the j pi e to the j 0, that's going to equal 0. And sure enough, that's what it is. You see, there it's 0 in the valley, and there it's 0 in the valley. You know, it's important to... I've said this before, and I'll re-emphasize it. You know, it's very important to be able to do a calculation and get the right answer. It's very important, okay? But it's also very important to be able to understand what you're doing, okay? You need to be able to do both. You need to understand it and be able to do the calculation. If you're like a super gee-whiz wizard calculator, it's still not that useful because, gee, a computer can do that, okay? And computers are not very, well, computers are very useful, but they're not very good. I mean, you go to it, you say, what should I have for dinner tonight? And it doesn't know, okay? It's not very good at answering open-ended questions or solving the kinds of engineering problems that people get paid for because, heck, you can just go buy a computer, and it's pretty inexpensive, and it runs all day long, and it doesn't ask for pay raises, okay? So if you want to bring something useful to the party, you have to be able to do something beyond what the computer does. So it's not just a matter of doing the calculation. You have to understand what's going on so you have insight that the computer doesn't have. Furthermore, just having beautiful insight is only so useful because if you may have beautiful ideas, but if you can't write them down on paper and nobody can ever get the right answer, and the Martian probe crashes into the surface of the planet because you didn't convert feet to meters, well, that's kind of not useful either. So you need to do both. You need to be able to have the intuition as to what's going on here and then correlate it with the equations and make the two align. And when you see, it's like programming. If you see something's wrong, if the thing crashes or gives you a programming segmentation fault, you need to go back and understand why. So if the equations are not aligning with your intuition, you have to try to understand what's going wrong. Is your intuition wrong? Is the equation wrong? So it's very, very important in this business. Okay. So, ordering of points in a plane. This is kind of interesting. Actually, there's a few of these interesting topics that expand into entire research fields that have kept the entire community of signal processing people busy for years. It's a wonderful thing. And ordering of points in a plane seems like a very simple problem that falls into that category. Another one was scaling of discrete time images and signals, right? We've made entire careers out of this. But in 1D, you can order the points in a plane in a 1D signal, right? And if I take one point out, if I remove it, what happens is that I've disconnected this set into two different sets. And in fact, I don't know how many people in the room have done this before. If you're done communications or in computer science, they do this too. There's a thing called dynamic programming, where you can solve optimization problems in things like optimal maximum likelihood symbol decoding for demodulation in modems, for instance, or if you want to in speech recognition applications, it's used also. But you can do a thing called dynamic programming, or the Viterbi algorithm is sometimes called, and you can solve this optimally by disconnecting the points, and you can turn what should be an exponential complexity problem into a polynomial complexity problem. It's very practical. It's actually solved on your cell phone when the cell phone's decoding the signal. Okay, but in 2D, everything breaks. Okay, because the ordering of the points, there's not a total ordering of the points in the plane. If I remove a point in the plane, it doesn't disconnect the set anymore. You can go around that point. Now, I can remove an entire row, and then I can do dynamic programming. But removing an entire row is a problem because the dimensionality of the row is high. So the dynamic programming problem still remains exponential complexity because the number of states is exponential. So there's this tension that occurs that you want to order the points in the plane, and you can order the points in the plane. You can order it with raster ordering, but if you use raster ordering, it's artificial, and you get distortions and artifacts in your results because you've imposed an unnatural ordering. On the other hand, you then get the advantages of a single causal ordering. The alternative is to try to retain some of the two-dimensional structure, but then usually things start to break. So this is a major area of ongoing research. It's never really going to be completely solved because it's a really fundamental problem. And it's inherited by problems in processing of signals on graphs, which is also an important area of research these days. But in any case, just to introduce you to some of the thoughts, one way of trying to solve this problem is to order the points in a 1D way. You can you can have quarter plane, so you can make each point only dependent upon a quarter plane. In this case, you have to decide which quarter plane. Is it going to be this? Is it going to be this? Is it going to be this or this? There's 4 possibilities, right? Then you can make it half plane ordering, so this point only depends upon the points that were in previous rows. Or you can make it the non-symmetric half plane, where it's as if you took raster ordering and then you used only points that were in the previous raster ordering. Okay. And this can also be flipped the other way if you raster in the opposite direction. So you could, instead of having these 2 points, you could have had the 2 points over here. Okay. Now, this ordering of the points is important when you do infinite impulse response filters. In an infinite impulse response filter, you use the results of the previous filter application, and the advantage of IIR filters is that they're much lower complexity for the same. You can get similar. Okay, the infinite with only a finite number of multiplies, you can get an infinite impulse response. With finite impulse response, if you do 2 multiplies per pixel, you only get a window of 2 pixels. So here you get more for your money, but it's much harder to control. So the design problem with IIR filters is more difficult. But if you can design the filter you need, you can get the same output with much lower complexity. If you remember, in your filtering lab, you did this, because you just used an IIR filter, and remember, you got an impulse response, which was huge, right? It took up the whole image. If you were going to do that with an FIR filter, it would have taken, if it's 1 million pixels in the image, it roughly takes 1 million multiplies per pixel, so it's going to be 10 to the 6th times 10 to the 6th. So 6. So it would be 10 to the 12th operations to filter the image, right? So it would increase the complexity of that filter by almost 1 million. So that's okay. See you next time. We're out of time. Bye.